Everyone, and welcome to this Quickwit presentation. Today we're going to talk about streaming ingestion with Apache Kafka and Amazon Kinesis. And I'm going to give it like a few more seconds for the presentation to buffer and more people to join. So I'll get started in about a minute. In the meantime, I'm going to introduce myself. There's not much to say. So my name is Adrian Gillo. I'm one of the three co-founders of Quickwit. I am based in New York City, where I moved 2 months ago. And so today we're gonna talk about the internals of the indexing engine. We're gonna look at the internals API that allow us to ingest files, but also ingest from streaming platforms such as Apache Kafka or Amazon Kinesis. Moving on to the next slide. So for the purpose of this presentation, I thought it would be easier to start simple, and we're just gonna talk about file ingestion at first, which will allow us to discover our internal APIs, and then we'll see later how those internal APIs are still very relevant to indexing from streaming platforms. So if you want to ingest a file with Quickwit today, it's pretty easy. Assuming you have the Quickwit CLI installed and you have created an index with the command Quickwit index create, then all you have to do as a second step is run the following command Quickwit index ingest, pass the index ID, and pass the path of a file, which contains new line delimited JSON documents. And this is going to start the injection of the file. So is there an issue actually with the broadcast? Let me check Discord quickly just to make sure everything's fine. Yeah, I don't see any issues, so I'm gonna keep on going. Okay, so what is this saying? Yes. So internally, we're gonna spawn an indexer, and an indexer is actually composed of what a chain of actors that we call an indexing pipeline. So I'm using the word actor because internally we have the internal actor framework, and so they communicate between each other between message passing. So we use the actor pattern pretty heavily inside Quickwit. And so the chain of actors start at the top with something that we call a source. And so for a file, it's going to be a file source. And it's going to do thing that's really simple. It's basically going to read the file line by line and emit batches of documents. So batches are basically groups of documents. This batch is going to be transmitted. Those batches are going to be transmitted to the indexer. And so the indexer is going to use those batches to produce the index. And it's actually going to produce pieces of index that we call a split. And a split is basically a small and independent 10TV index. 10TV being the indexing library that powers Quickwit. And so eventually your index is going to be a collection of splits. So the indexer, the second actor on the chain, is going to take the raw batch documents and produce splits on the local drive, and then it's going to upload them to S3 or any other cloud storage, and then finally it's going to commit those splits to the Metastore so that they become available to the searchers. So let's take a look at this in the diagram. I don't know if you see the cursor. So as I was saying, you start with the file. The file is read by the file source. The file source emits DocBatch. batches of documents. The structure that we use internally within Quickwit is called a DocBatch. The indexer ingests those DocBatches, uploads, produces splits locally, uploads them to S3, and then commits them to the Metastore. So I should have said one upload to commit. And now, if you take a closer look at the source trait, all you have to do is to implement a new source, is implement the training phase and the source training trait, basically. And the main method, there are several, but the main method is emit batches. And the signature looks a little bit complicated, but at the end of the day, you have a mail. The source has a mailbox. And all it has to do is like put some DocBatch in the mailbox, and the rest of it is like mostly boilerplate for like knowing what's the status of the source, perform like health checks, all that stuff. But at a high level, it is like really simple things. Now, if you take a look at the DocBatch structure, it's actually fairly simple. It only has 2 attributes. No surprises on the docs attribute. It's just a vector of strings, which are your like raw JSON documents. And the more interesting attribute is actually checkpoint data, checkpoint delta. So what is this checkpoint data struct? The checkpoint delta struct is one of the structure that are part of what we call the checkpoint API. And so the checkpoint API is the mechanism that Quickwit uses to achieve idempotency. What a checkpoint in Quickwit is a way to keep track of the position of the last ingested document. And if I want to be more precise, it's not just ingested by the indexer, but published. The checkpoint is a JSON object stored in the Metastore. And you're going to tell me you're using a type language Strata Trust. Why do you use JSON? Like, would it be better to like have something like a bit more rigid? And actually, it's really convenient for us to use JSON. It gives us more freedom to have like a different serialization of the checkpoint depending on the source type. So the serialization format of the checkpoint within the Metastore depends on the source type. So for a file source, it's really simple, right? Like if you want to keep track of where you are in a file, basically you need to know where the file is. So you keep track of the absolute file path, and then you keep track of the offset in the file. And so the checkpoint basically is where you are currently in the file or in the stream. The checkpoint delta is the data structure that encodes an incremental update to the index. And basically within the DocBatch, the checkpoint delta keeps track of where the first document is in the batch, and where is the last document in the batch. And we're using half open interval for that. So from is exclusive, to is exclusive. And so when you want to commit new data to the index, basically you apply a checkpoint delta to the checkpoint to update the checkpoint. And the Metastore ensures that the checkpoint and the checkpoint are actually compatible. So what does that mean to be compatible? Let's take an example. So let's assume you're just ingesting some data from a file, and the value of the current checkpoint is 12. Let's just say like 12 is the offset in the file. If you have a checkpoint delta that goes from like 10 to 42, you want to reject this checkpoint because 10 is lower than 12, which means that it's basically overlap. And so if you were to accept that delta, you would basically have like duplicate data within the index. So you want to reject that delta. If on the contrary, the checkpoint delta starts at 12, exclusive and goes later in the file in the stream, you want to accept that checkpoint delta. And so after applying the checkpoint delta to the checkpoint, the new value of the checkpoint will be 42. If this is the last case, if the checkpoint delta starts at 14 in this example, so after 12, we still want to accept that checkpoint delta, but we display a warning. Why do we display a warning? Because basically 14 is like higher than 12, so we basically detected a gap in the stream. So for a file, it's a little bit worrisome, but actually for streams, it's a legit use case. Like, assume you're ingesting a stream, and then for some reason indexing is paused for a few days or for like a few hours. After a few hours or a few days, depending on like retention rule, like maybe retention would be applied, and you would start losing data from the low watermark. So if you were to resume indexing later, you would start at a higher mark than the checkpoint, and this is like so that this is still a valid checkpoint, and that's why we want to accept those checkpoints, even though we detected a gap, and that's why we display a warning of the gap. This is not a feature that we have, but we could like have like a flag that says struct, and we would basically fail and warn the user when we detected a gap. So far, people haven't asked for this feature, so we haven't implemented it, but it would be pretty easy to do. So let's take a look at the Metastore API quickly. All you can see is it's fairly simple, and it's really just about telling the Metastore which index you're updating, from which source, which are the new splits, and what is the value of the checkpoint delta for that index increment. And as you can see here, this is copy and paste from the code base. Like we do encode the checkpoint incompatibility in the Metastore errors. So we talked about files, so let's talk about distributed queues. If you look at the properties of distributed queues, usually they guarantee message ordering, they maintain a position for its message, and the position increase monotonically. So if you think about those properties and how you like use file APIs and how you navigate through a file, you realize that distributed queues offer a very file-like API, and it seems like we're going to be able to reuse that checkpoint API for even distributed queues. So some people also, like right now, as I'm saying that, some people are thinking, wait a minute, like a stream is a bit more complicated because you have partitions of shards, and what we can just say is basically, well, it's akin to keeping track of the offset within multiple files. So if you look at the checkpoint for Kafka source, it's very similar to the checkpoint that we saw before for a file. The only difference is that now we keep track of like many of the offset of many partitions. But really, it's the same mechanism and it's the same API. So a checkpoint delta is gonna keep track of like many partitions instead of just like one file if it's a file. And now I want to talk briefly about implementations, and I'm going to talk about the Kinesis implementation first. So as we just said, like a Kinesis stream is composed of multiple shards. So behind the hood, what we have to do is to spawn a Kinesis source that itself spawns a pool of shard consumers. Each shard consumer is going to pull the shards and forward records to. Okay, I'm back to slide number 2. Don't know what happened here. All right. So yes, shard consumers are going to consume the shards as the name implies, and then forward the records to the Kinesis source. And then the Kinesis source has just two jobs, just like batch those records together in DocBatch and just keep track of like where we are in each shard and through like the sequence number mechanism. And so we keep track, it updates the checkpoint delta and then sends just DocBatches. So I think I have a diagram for that. So here you can see that this is a map. This is basically one-to-one mapping between a shard and a shard consumer. The shard consumer forward records to the Kinesis source. And every time you see an arrow, basically, we're using it's an actor sending a message to another actor, and we're basically using like channels. The Kafka source implementation is actually much simpler because all that bookkeeping and that logic for like each partition is actually encapsulated by the Kafka client that we use. It's a Rust RD Kafka, which is basically binding over the librd Kafka, which is I think it's a C library, and so it implements the stream interface. And for like the implementing the Kafka source, we had like less much work to do. I want to talk about the state of like distributed and non-distributed indexing. So our last release from last week, Quickwit 0.3, does not support distributed indexing. What happens is when you spawn a source or a Kafka source or a Kinesis source, it's going to list all the partitions of the shards for the stream that's described by the source parameters, and it's gonna start ingesting the data. So what may happen is if the rate of data that's landing in the stream is faster than our indexing throughput, then the Quickwit indexer is going to start lagging. And our indexing throughput is between 20 and 40 megabytes per second. So if you are over that rate, the indexer is going to lag. And so I'm gonna talk about the solution that you have at your disposal in this release and in the upcoming release. So in the last release, there's not that much you can do, unfortunately. Like all you can do is like vertical scaling. So you can add more threads, basically like get a beefier machine, more CPU. You have like more CPUs available, so you can just allocate more threads to the indexer. When you do that, just make sure you also like bump the memory a little bit. What really matters is the number of threads, not that the memory that much, but you still want to increase the memory. And then the other knob that's available is increasing the commit timeout. So the default value in Quickwit is 60 seconds. So every 60 seconds, you're going to commit a new split. Every 60 seconds, you're going to commit a new split, or if you reach a limit of documents, you can commit earlier than that. If you increase those values, like those commit threshold, you're gonna basically commit less often, and it's gonna help the indexer basically streamline things a little bit easier, and it should help a little bit. But in this release of Quickwit, like you can't do that much, unfortunately. Quickwit being like a really young project. But things are going to get better, and this is why I want to talk about the next release. So what we want to do in the next release is manual horizontal scaling, which is better. It'll work with Kubernetes, and so with Kubernetes with a stateful set, we'll be able to have like multiple indexers running in parallel, and they'll be numbered. So you have indexer 0, indexer 1, indexer 2, And so we'll give the user the ability to like say, hey, I want that source to be on this indexer, and within that source you could actually allocate which charge of partitions. So typically you could be saying, okay, I have like that big Kafka topic going from like, I don't know, like partition 0 to 10. I can allocate manually the first 5 partitions to indexer 0, and then the 5 remaining partitions to indexer 1. So you'll be able to do that manually in Quickwit and the next release of Quickwit. Later in 2023, what we want is like fully automated distributed indexing. So basically that logic that I've just described of like you manually building ranges of partitions and then assigning them, we just want to automate that work. So in Quickwit, eventually we will do that automatically for you. And so you don't have to do that manual work. That's all I have in terms of like presentation. Now we're gonna I'm gonna do a little demo, and let's see if this is probably too small. Let's see if the curse of like the live demo is gonna hit me. All right, so makes it this bigger. A lot of terminals open. So in this terminal, I actually can't see I have a double screen set up, and I can't see my screen with my laptop in front of it. So I'm sorry, in case you're gonna see me sideways, I'm gonna turn so you can see me better. So in this tab, in this first tab, nothing real interesting. I have like a basically, so I'm gonna run a local, okay, so what is the demo? The demo is me adding data into a local Kafka cluster, and then we're just gonna ingest this data from the Kafka topic to Quickwit, and I'm gonna observe like splits being added to the index. So first tab, not real interesting. We have local Zookeeper deployment. Second tab, my Kafka broker is running. Third tab, I'm gonna use it to create a new topic. So let's list the topics right now. I just have that one topic, which is like for consumer sets. It's a topic for internal use for Kafka. So let's create a topic. Yeah, the data set that we're going to use for this demo is the GitHub public archive. So I'm gonna create a topic with 3 partitions called GH archive. So here it is. I'm gonna create this topic. Yeah. I'm gonna list it, and I'm going to describe it. So far so good. Now I'm going to put some data in the topic. So let me show you. If I LA, I have a bunch of JSON files that were like just downloading from the GitHub archive, and so I'm just going to unzip them and load them on the fly into the Kafka topic. Let me make this bigger. So that's the command I'm using. I'm actually using command from the Kafka tutorial. So if you want to do this at home, you just have to go to the Quickwit tutorials webpage, find the Kafka tutorial, and just do the same things pretty much. So if you look at Kafka, it's actually doing this thing. Just want to highlight that I have to do a little bit of JQ for this to work, because right now Quickwit is missing a Boolean field and a date field that is flexible to ingest any kind of format. So I'm doing a little bit of JQ here to make it easier for Quickwit to ingest the data. But we're gonna have those fields in the next release, so pretty soon you won't have to do that. Now I'm gonna create an index. Let me make this tab better. So I'm using Quickwit 3.0 locally. I'm just using cargo run. So the command I'm running is index create index config. So that created, I have a bunch of logs, but here you can see that I created GitHub archive file. I can show you the content of the config. Config, tutorials, index config. So bigger. So index ID, GitHub archive, just a bunch of fields like the ID. The ID. What's interesting is I think the payload we're using the JSON type, so it's gonna automatically ingest the JSON data without me describing explicitly the schema. So I'm making use of the new feature of the new schema indexing feature. It's really handy because like the schema of these data sets is a bit complex, so it saves me a lot of work. And what I did is I set the commit timeout to 30 seconds. So we should be processing a split every 30 seconds. And I'm just saying that this data set is shared. It has a timestamp field. That timestamp field is called created at. So here we are. So now I need to add a Kafka source. So I probably have a command there. Yes, I had it here. Source config. Okay, so I'm running Quickwit source create, specifying the index, GitHub archive, and the Kafka source config. So here it is. Let's take a look at this config. It's pretty straightforward. So source ID, Kafka source type Kafka, and then we want to consume from the GitHub archive topic and use my local Kafka cluster. So now I'm just going to run Quickwit run, and it's going to start indexing data. So we're not going to see much for like the first 30 seconds, unfortunately. But what we can do in the meantime is like describe the index. So if I describe the index now with the index describe command, what I see is like I have 0 splits, 0 documents. And as we are publishing new splits, I'm going to rerun that command. You're going to see how the index is evolving. So here we are. We just, you can see from the logs that we just started a new split, and we just committed the first split. You can see here in the logs that when we publish, you can see basically the checkpoint delta. So checkpoint delta is saying like, oh, for partition 0, we're going from, whoops, it's going up. I lost it, but basically, yeah, like for this offset, say I'm going from 0 to, and so on and so forth. That's how to keep track of it. So if I run another describe now, this time I have, this bigger again. Now I have like splits, and so the size of the number of documents in the index is increasing. And so I think this for this data set, we're just going to produce 5 split, I think. Last one I ran it. I mean, for this segment of the data set, it's not the whole data set. It's just a few hours of data. So now we can run queries. Now we have 3 splits. So let's just run this query. So I'm just doing a curl on the search API endpoint. And my query is like, give me all the events that have the login or the login Kubernetes. And also the repo Kubernetes. So I'm just GQing it to get the number of hits. So I have like about 700 hits right now. We can see the data in greater detail. But for instance, this event is a pull request event from who? I don't know, from a user called Nikita. Those are like GitHub events. Let's see. Yeah, and so I've just rerun this query, and in the meantime, we had a new split, so you can see that the number of hits is increasing. And finally, I'm going to run an aggregation query where basically I'm going to group the events by event type. So it's this query that you can see. So it's just the filter on the events is the same, which is interesting, like the Kubernetes events. But this time we're going to group them by event type. And so here we are. And so, for instance, you can see that you had like 2 delayed events, 7 create events, 21 push events for the interval of time. How long was that interval? Yeah, for 5 hours. In 5 hours, you have 25 new issues on 25 issues event on Kubernetes. That's it's confirmed it's a fairly successful project. Hopefully, Quickwit will get there one day. That's all, folks, that I have for today. So I'm going to leave it for question now. No question, which is fine. I'm just going to give it a few minutes, and if we don't have new questions by then, I guess I'll wrap up the event. So you may have seen, in the meantime, I'm just going to say random stuff. You may have seen me play with this. I have a bunch of toys around my desk that I'm using when I'm thinking about something. I need my hands to be doing things. So this is one of them. It's a little egg that I press with my hands. All right, I guess that's it. Thank you for joining the events. If you have more questions, we're always available on Discord, on discord.quickwit.io. Feel free to try the product, obviously. Open issues if you have problems using the Quickwit. They're too small. All right. That's my egg. I've just moved in, so probably have some other in one of those boxes. Oh, here it is. All right, so might as well have a duck, rubber ducking. So I actually rub ducks when I'm stuck. Rubik's. Actually, so yeah, like I said, just moved, and those were in a box for like 6 months. So I actually forgot how to solve them. But I'll get back quickly. I think that's it. Maybe I'll keep more toys for the next event. All right, folks. Have a good one, and enjoy the rest of your day wherever you are. Bye-bye.